In this video, we're going to look at the semantics of PL. So in SL, the smallest unit is the sentence letter, and this has no internal structure. So whether sentences are true is determined by truth value assignments. Because the truth value assignments just assign values true or false to the sentence letters, the smallest units in the language, and then we just work up from there to determine the truth values of everything else. In PL, because of the fact the sentences are built up from smaller parts, we need something more complex to determine their truth values. These more complex things are interpretations. And what they do is they give meaning to all the parts of the sentences, predicates, constants, and so on and so forth. There are two types of interpretations, formal and informal. So an informal interpretation, these are the different parts. You have universe of discourse. You have a meaning for each predicate, specifies precisely which objects in the UD each predicate applies to. And then for each individual constant, you have one object in the UD that it names. And then on the basis of this, you can go through and you can figure out what truth value every sentence is going to have. Now, formal interpretation, um, so the main difference between informal and formal interpretations is this, that instead of giving a UD by description and giving the meanings of the predicates, what we just do is we specify sets of objects for these. So we specify a set of objects that makes up the UD, and we specify for each predicate, we specify a subset of the UD that each one is true of. So we don't worry about what the predicates mean. We're only concerned with which objects in the UD they are true of. Then, once we have this, the formal interpretation has very rigorous procedures for evaluating quantified sentences. In an informal interpretation, these are, kind of looser. Since this is an introductory course, we're only looking at informal semantics. But then if you go on to do, further logic courses, you will be working with formal interpretations. So the universe of discourse, the one restriction on it is that it has to be non-empty. It has to have at least one object in it. Other than that, there's no restriction on what objects that it contains, as long as it's clear what objects they are, right? Like what is in the UD, as long as this is clear. For predicates, each predicate has to be specified precisely, so you want to make sure that you're not giving ambiguous or vague interpretations of predicates, right? You want to make sure that it's clear what each one means. For example, say your universe of discourse is mammals, and then you decide you're going to interpret BX as X is big. Well, what is a big mammal, right? Like what counts as being a big mammal, right? That's not specified, right? That, which animals are big, which animals are small, right? This is something that's, really unclear. And even like, what about, say, an obese squirrel? I mean, squirrels are small, but an obese squirrel is unusually large for its species. And that's actually a legitimate interpretation of being big. So does that count as being a big mammal? Um, this is just not going to work as an interpretation of a predicate, right? You need to indicate more precisely what B means than just saying that it's big. Um, Note that this is also basically the standard for whether your universe of discourse is specified precisely enough. All right, so as long as you can figure out what the extension of all your predicates are, then your universe of discourse is precise enough. If your universe of discourse is vague enough that you can't make sense of whether, what objects your predicates apply to, then you need to make your universe of discourse more precise. Now, with constants, each constant has to name exactly one object. It always needs to be clear which object it names. So if you just have a constant like, say, G is guy with sword, um, well, I mean, in a lot of universes of discourse, there's going to be more than one guy with sword. So it's not clear which object it names. Um, you know, person holding sword is properly speaking a predicate because there's more than one of them. Again, in many universes of discourse. So again, that would mean that the constant would be referring to more than one object. Um, Now that is actually Aragorn from Lord of the Rings, and sort of illustrates something else that we have, right? Which is that more than one object can name, or more than one consonant can name the same object. Um, in fact, actually remember that the only stipulation on universe of discourse is that it has to have at least one object in it. If you have a universe of discourse that only has one object in it, then every constant names the same object because there's only one possibility there. Um, but so Aragorn, if you've read Lord of the Rings, you may remember when he introduces himself to the hobbits, he actually introduces himself by saying, "I have many names." And we can do that in an interpretation. You just have many constants, and all of them refer to Aragorn. That's perfectly fine. Um, Note that this is actually not an exhaustive list of Aragorn's many names. I just ran out of space. Um, Okay, remember though that the variables are W, X, Y, Z, right? They're the ones that go inside the quantifier symbols. Variables are not constants. You don't assign those meanings in an interpretation. Hmm. Um, one one useful way of avoiding ambiguity is to use simple mathematical interpretations. You're not required to do this. It's just it's handy because everything's just very precisely defined, so it is really hard to end up with interpretations that are too vague if you're doing it that way. Um, and make sure, though, if you're doing this, that you use simple mathematical interpretations because this is an arts course, and we only work with very, very simple math, right? Many art students have not taken any math since high school. Um, I guess I've at least taken, well, I did first year calculus in university, but still, that was 25 years ago. So, if you're thinking of putting something in an interpretation like, say, logarithms, just remember that for the past 25 years, at least for me, um, my only contact with logarithms would be that in my calculator app, there's a little button that says log on it that I have never clicked on. So yeah, so there's that. Um, if you are an arts major like me and you want a refresher on really basic facts about math, like which numbers are which and stuff like that, there's an appendix in the back of the textbook that just goes through like some basic facts that are useful for when you're constructing interpretations. Um, okay, so here's an example interpretation. Universe of discourse is the positive integers. These are the counting numbers that start with 1 and then go up. G is strictly greater than, L is strictly less than, EX means X is even, OX is X is odd, and then we've got constants A, B, C referring to the first 3 numbers. I'm not worrying about anything bigger than that. Okay, now we're going to use this interpretation to illustrate the truth conditions of like various sentences in PL. So atomic sentences first. Atomic sentences, remember, this will be an n-place predicate followed by n individual constants. And basically, what makes an atomic sentence true on an interpretation is just you look at how it's been interpreted and whether it's interpreted as a true or a false statement. So like take, for example, GAB, right? So G is strictly greater than, A is 1, B is 2. So what this means then is 1 is strictly greater than 2, which is false. So this statement here is false. If you have EB, EX is X is even, B is 2. So this says that 2 is even, which is true. Truth functional compounds, these are functions of the truth values of their components, exactly the same way as in SL. So take this, for example, EA or EB, right? E is even, A is 1, B is 2. So what this means then is 1 is even or 2 is even. And that's true because 2 is even. It's got one true disjunct. EA implies LCA. So that is one is even. That's the material conditional. LCA, this will be X is strictly less than Y, where the X is C, which is 3, and the A is 1. So here what we have then is if 1 is even, then 3 is strictly less than 1. And note here that this is a material conditional with a false antecedent because it says that 1 is even. And so that's true because every material conditional with false antecedent is true. Now, before we get into the truth values of quantified sentences, we need to introduce this notion of satisfaction. So if you have an open sentence like OX, right, X is odd, what this does is it specifies a condition, being odd, that objects in the universe of discourse can satisfy or they can fail to satisfy, right? So in this particular case, right, being odd is satisfied by 1 and 3. It's not satisfied by 2. 2 is not odd. Now, what you probably would want to say here, and admittedly, this is often the way that you'll be thinking about this, is that OX is true of 1 and 3 because they're odd, and it's not true of 2 because 2 is not odd. The thing is that this is technically not right because OX isn't a sentence, and it doesn't have a truth value in PL, so it doesn't, strictly speaking, make sense to talk about OX being true or false at all. This is why we have this notion of satisfaction, right? We don't see this as being a sentence that's making an assertion that can be true or false. We see this as providing a condition that an object can satisfy or not satisfy. Um, which is what we need then for making sense of the truth conditions of the quantifiers. So we'll look at existentially quantified sentences first. If you have an existentially quantified sentence, this is going to be true if and only if there's at least one object in the universe of discourse that satisfies the part that's inside of the quantifier, the P part, right? So for example, there is an X, EX. EX is X and E is even. So what this means then is basically just this. There is an even number. So it's going to be true if and only if EX, this condition here, is satisfied by at least one object in the universe of discourse, which is true. Or, well, yes, it is true. I mean, that is satisfied by at least one, right? 2 and 4 and 6 and so on and so forth. So this is true. If you have this, then there is an XLXA. So what this means then, this is, remember, strictly less than. What this means then basically is there is a number less than 1, right? There is an X such that X is strictly less than 1. This will be true if and only if there's at least one object in the universe of discourse that satisfies LXA. So, in which that number is less than 1. 1 is the smallest of the positive integers, though, so this is actually false. For universally quantified sentences, sentence that is universally quantified is true if and only if every object in the universe of discourse satisfies the formula inside the quantifier. So take this, all right, for all XEX. What this says is basically just every number is even, right? So it's going to be true if EX is satisfied by every positive integer. And as soon as you hit the first one, right, 1 does not satisfy that, so this is false. For all X, X is, or GXA, right, X is greater than A. Every number is greater than 1 is what this means. It's going to be true if every object in the universe of discourse satisfies this condition of being strictly greater than 1. Unfortunately, we're talking about strictly greater than, not greater than or equal to, which means that this is false because 1 itself is a positive integer and 1 is not greater than itself. Now, one way that you can think about the truth conditions for quantified sentences is like this. Um, you can imagine an existentially quantified sentence as being sort of like an infinitely long disjunction. So you take the formula inside the quantifier, and then you put in a name for each object in the universe of discourse. And when you're looking at an infinite universe of discourse, like the positive integers, this is going to be an infinitely long disjunction. Um, so, for example, there is an x ex, right? There is an even number. You can imagine this as being a disjunction like 1 is even, or 2 is even, or 3 is even, or 4 is even, or so on and so forth for every one of the positive integers. And then you evaluate whether this is true. And an infinitely long disjunction, if one of those disjuncts is true, then this is going to be true. This incidentally, this was an idea that was proposed by the philosopher Ludwig Wittgenstein as a way of understanding the truth conditions. And as a definition of the meaning of the quantifier, it doesn't really work. But it's still like a useful way of thinking about it. There's an analogous way of thinking about the universal quantifier. You can imagine a universally quantified sentence as an infinitely long conjunction. So for all x ex, you understand this as being a conjunction like this. 1 is even, and 2 is even, and 3 is even, and 4 is even, and so on. And then you evaluate this by just looking at, I mean, is every conjunct in this conjunction true? Um, all right. We're going to end this off by talking a little bit about categorical sentences and how they work in this framework. So one thing to note, first of all, is that when you have A and E sentences, these are the universally quantified categorical sentences. These are in fact true of every object in the universe of discourse. That's one of the reasons why you set them up in the way that you do. So take this E sentence, for example. No even numbers are odd. Right? Here's how you would symbolize this. For all x, if x is even, then x is not odd. Then if you look at this formula here, right, this is in fact satisfied by every positive integer. For each positive integer, if it is even, then it is not odd. And another way that you can think about this is remember that by the rule of implication, this is actually equivalent to this. Right. So this here then is saying, this is another way of understanding this condition, right? It's saying then that um, for every x, right, either x is not even or x is not odd. And again, this is true of every number. You look at each number, right? Either it's not even or it's not odd. That's going to be true of every single one of them. Okay. This thing we'll look at. So in a previous video, we were talking about categorical sentences about things that don't exist in your universe of discourse and how those work. And so now I'm actually going to prove what I was saying about this by showing, using the truth conditions, how these work out. So we're going to use this universe of discourse here. The universe of discourse is going to be animals, and we'll just specify that it's real animals, which I guess might be, I mean, it may seem sort of redundant, but we did have a universe of discourse previously that was characters in Lord of the Rings, so maybe we do need to specify that we're talking about real stuff this time. Gx is x is green, and tx is x is a Tarantagopher, which is something that I just made up. Note that for the purposes of the illustration we're trying to make here, we could have actually just left the universe of discourse as the positive integers because there are no Tarantagophers in the set of positive integers either. Okay. So let's look at the way that certain various things work out on this, right? So there is a Tarantagopher. There is an XTX. If you look at the set of real animals, none of them are Tarantagophers, so this turns out to be false. Okay, how about no Tarantagophers are green? Well, so this is how you would symbolize that E sentence, right? So then you look at the set of real animals, and whether this formula here is satisfied by each one. And the thing is that because of the fact that Tarantula gophers aren't real, um, for each member of the universe of discourse, right, for each animal, it's not a Tarantula gopher, which means that the antecedent of this conditional is false, which means that the conditional as a whole is true. So for the entire universe of discourse, actually, this turns out to be true. Um, and yeah, so this E sentence, no Tarantula gophers are green, turns out to be true on this universe of discourse. Because of the fact that this is in fact satisfied by every animal, because it's not a Tarantula gopher. However, by the same reasoning, all Tarantula gophers are green. This is also true because, again, this conditional isn't satisfied or is satisfied by every uh, every object in the universe of discourse because they're not Tarantula gophers, which means that this one also turns out to be true.